this is a very interesting question. So we're looking at essentially a practical application of photon momentum, which is propelling a space probe using a solar sail. Now, we're asked to figure out how many photons are required in order to accelerate the probe by 1 meter per second. So, we know from the previous question that the momentum of each photon, so say p photon, is equal to 1.33 times 10 to the minus 27 kilogram meters per second. And we are also interested in, so now since we know that, we want to figure out how many of these striking will transfer essentially enough momentum to the probe for it to be traveling at 1 meter per second. So at 1 meter per second, the momentum of the probe would be mass times velocity, which in this case is 500 kilograms times a velocity of 1 meter per second, which equals 500 kilogram meters per second. Now, there's something very important in this question that you need to pay attention to, and that's the fact that the sail is perfectly reflective, so the photons are undergoing an elastic collision. So what this means is, you have your space probe sitting here, and a photon will arrive, as so, and then, so it'll have some initial momentum, so we'll call that like p gamma for the photon. So that's the original situation. Now, the final situation is that the photon has been reflected and it's transferred momentum to the probe. So the photon is now moving out this way, and that's just going to be, because it was reflected with its exact initial momentum, it's now got minus p gamma as its momentum. So that's the photon leaving. The space probe will have to have a momentum. So we've got to have momentum conserved here. So we've got p gamma to the right at the start. We've got to have that same thing at the end. So this is going to be 2 times the momentum of the photon. That's how much the space probe gains, in order that the total momentum in the system is conserved. So what that tells us is that so we could compare this, for example, with, say, the photon was absorbed, and that was just a straight transfer of momentum. If we ended up with no momentum in our photons at the end, we would essentially have just p gamma to the right instead of twice that. So it's actually very beneficial to have a reflective surface on a solar sail like this. Real ones that they would be using probably wouldn't be 100% reflective. Any realistic one is going to have some kind of inefficiency. But the intention would be to get as close as possible to perfect reflectivity. Now, how can we use this to perform the calculation? Well, we're essentially saying how many of these photons do we need to go into the final momentum of the probe. And remember, because each photon essentially gives the probe twice as much momentum as it itself has, we are going to divide our number of photons by 2. So let's figure out how many photons would go into 500. So we've got essentially got 500. That's the momentum of the probe, and we'll divide that by how much momentum each photon has. And we'll also put a 2 on the bottom, so we're essentially dividing by 2 for the logic we discussed before. And if you perform this calculation, you will end up with 1.89 times 10 to the 29 photons. So that's how many photons would need to strike in order to create the amount of final momentum and velocity that we wanted.